Okay, we're going to start looking at reaction types in a sort of different viewpoint. We've looked at synthesis, decomp, double replacement, single replacement, acid base, which is neutralization, which is just a double replacement with acids and bases, and combustion. And combustion always forms.
Carbon dioxide.
Yes, combustion reactions always form carbon dioxide and water. But combustion reactions also, as we showed you on Tuesday, also release a lot of heat, which we would say energy and light, okay? Because energy is light and heat, sound. Those are all different types of energy, but it releases energy. All right. So molecules are held together by these chemical bonds. How do you break a bond? If I have a piece of paper, this is bonded together, how do I break it? You rip it, but you have to put energy in to break the bond. Okay? So breaking bonds requires energy. So you have to add energy to break a bond. Now, if somehow I could reform this, all right, there would be a release of energy. Okay? So when you form bonds, you release energy. We call the bond energy, has a special name in chemistry. It is called enthalpy. Py, not pli. Enthalpy. And it's given the symbol. What do you think the symbol is? You want to say E, don't you? You know what we call it? H. Because I think E would get confused with energy and things like that. Okay? So the bond energy is called H, enthalpy, or is symbolized by H, enthalpy. Sorry?
That's a question that you will take us on. What is entropy?
Randomness.
What?
I'll tell you after. All right. When there's a change in bond energy, okay, all right, due to a chemical reaction, it's a change in enthalpy. And if you've taken physics, you should know that a change is symbolized. You don't say change in, you write. Does anybody know what you write?
Delta.
You write delta. So we would say delta H is the change in enthalpy or in bond energy. Okay. And you remember the other day I said there's an activation energy. You have to put some energy in to break the bonds. Like sometimes a reaction just sits there, but as soon as you add a little bit, like when I burned the bubbles, they just sat there. But as soon as I added a tiny bit of energy, that activated the reaction. So we call that the activation energy. Which is the minimum amount of energy required to get the reaction going. Okay? Looking at energy, there's two types of chemical reactions. There's the kind that release energy and the kind that absorb energy. The kind that release it are called exothermic. That is a release of energy. I should say a net release of energy. And endothermic, which we also looked at the other day, is a net gain or net absorption. Absorb. I can't spell. I spell absorb.
ABSORBTION.
Absorb because it's it's B T I O N. A net absorption of energy. There we go. And that was the two that I mixed together, and you put it on your hand. It was like the instant cold packs that they have, or the chemical cold packs that they have. Okay, we'll look at potential energy diagrams in a sec. Let's just look at this from a visual point of view here. You've got react, so we're going to do AB reacts with, ignore that, CD, and we're going to get AC, and we're going to get, or call it AD, and we're going to get BC. This is the reaction we're going to look at. So AB is sitting there, bonded together, and we reacted with CD. They're just sitting there in a flask doing nothing. Okay? You add a bit of energy. Okay? What is a chemical reaction? We talked about this right at the beginning of the unit. What is a chemical reaction? How does it start? It's a collision, right? It's the molecules colliding with each other. That's why you have to add some energy, because that gets the molecules to slam into each other with enough energy and in the right orientation to actually react. But when they do, what happens is the chemical bond to A and B starts to weaken, all right, and CD. Why are you not? And C, whoops. And the bond between CD start to weaken. Okay, that's what the dash line represents, is the bond starting to weaken, and they start to form new bonds. I should have written this the other way. I'm going to reverse those two. Sorry. Like that. There we go. And bonds start to form between the other atoms or molecules. Okay. All right. So this is all happening in a very, very short period of time, obviously. But this intermediate form is called the activated complex. So you get this sort of chemistry, you would call this like a resonance structure, which means the bonds are all sort of changing at the same time. And then if the reaction proceeds, the AB bonds break and the DC bonds break, and these form new bonds. And so you get A bonded to D, and you get B bonded to C. Okay, and you get your products. So these are your products. Obviously, this all happens in fractions of a second. Okay. So over here, the reactants, the bonds have to be broken. Bonds broken. This takes energy. And the products, the bonds are formed. And when you form a bond, you release energy. Okay. Whenever you're forming bonds, you are releasing energy. Okay. So what determines if it's endothermic or exothermic? Okay. You okay with this? Going once, going twice. All right. Endothermic means energy is put into the reaction, a net gain of energy, a net absorption. All right. So, in an endothermic reaction, we absorb energy from the surroundings. That's the cold pack demonstration I did the other day. It leaves everything in the surroundings cooler than the beginning because we've taken energy. If you're measuring it in sort of temperature, right? It could be light energy, it could be anything, but we're going to think of it as temperature. Now I'm going to leave this blank and we'll look at it in a sec. Endothermic reactions tend to be non-spontaneous. Okay, because they need to absorb a lot of energy or some energy to get going. So in a diagram, what does this look like? So I'm going to expect you to recognize what's an endothermic and exothermic based on the energy diagram that we're going to do right now. Okay, so we have the potential energy here, and we got the reaction progress, like how it moves through the steps. So 20 kilojoules. These are in kilojoules because it's in energy. These are the reactants. Okay. Now, what do you have to do to get a reaction going? You got to put in energy, right? To break the bonds. What do we call that energy that you have to put in? I've said it a couple times, but probably didn't emphasize it enough. The activation energy. Okay. So we have to put energy into the reaction. Okay. And we'll just call that 60. So this hump, this distance here, we're going from 20 kilojoules. This is the resting, happy potential energy state of the reactants. If I want it to go to react, I have to get it up to 60 kilojoules. So I'm adding energy in. So it's pulling it from the surroundings, or you're adding heat to it or something. That is the activation energy. Which we call EA. Okay. EA is the activation energy. How much energy do you have to put in to get the reaction to the hump, to get it to react, to form the activated complex? All right. This is the top of the hump, the activated complex. I'll write that in there in a sec. Okay. Then once it gets to the activated complex, it forms new bonds. When you form bonds, what happens? You are releasing energy so you become more stable. Okay. So this is the peak, and then it falls to whatever the stability of the products is. So these are the products here. Okay. This is the, come on, activated wow. There we go. That's the activated complex at the peak of that little hump. All right. You add in the energy, you start to break the bonds, start to form the bonds if you want. So if this is AB plus CD, this little peak here is A to B, C. It's when they're all starting to form the activated complex, okay? And then you get to the products, which we'll call AC plus BD. Whatever, it doesn't matter. Okay? And then you release the energy. Now we got to look at some of these things here. Activation energy, EA. What is the activation energy? How much energy do I need to put into the system to get it to go?
40 kilojoules.
It's 40. It's from here, what you started at, to the top of the peak. That's the EA. So in this case, I'll just say, I'll actually write it out, 60 kilojoules minus 40 kilojoules minus 20 kilojoules equals 40 kilojoules. That's how much energy I have to add in to get to there. Okay? Does everybody understand that? It's just the top minus where you started at. Okay, so I have to add 40 kilojoules. If you add 35, this reaction doesn't go. Okay, if you add 48, the reaction goes, but you've added extra energy that you didn't need to. Okay, you just have to add minimum of 40 kilojoules to get the reaction to go. Delta H, so this is what determines if it's exo or endothermic. Delta H is the change in enthalpy, right? Change in enthalpy, which is potential energy of the products minus the potential energy of the reactants. What's the potential energy of the products? I guess we got to make up a number here. What is that? 30? 20? 40? 40. Looks about halfway. So the potential energy of the product, you just go across, is 40. Minus, what's the potential energy of the reactants? How much? What was it what you started at? It's 20. So 40 minus 20 is 20 kilojoules. Okay. Does that make sense? That is the change in enthalpy. If this number is positive, it means it is an endothermic reaction. Okay? If your delta H is positive, it's an endothermic reaction. All right? Tomorrow, we'll look at exothermic and then move on.